Okay, this is going to be section 5.2, which is applications. Applications of maxima and minima. So, how am I going to do this? Okay, so I'm going to be working through the 4 examples that I have in the 5.2 lecture, which is on Canvas. So instead of recording myself writing all of these out, as you're watching this video, just have this PDF open in another tab. That's going to be the easiest way. So example 1 says, I will note it as example 1. We've got a clothing company that manufactures hockey jerseys. It can manufacture them for sale to college bookstores in runs of up to 500. So that's not a cost. That's saying that each time they manufacture these, they can do them in bunches of 500. It costs in dollars for a run of these jerseys. So a run, I guess we can think of that as a delivery, is C of x. So this is a cost function. C of x equals 2,000 plus 10x plus 0.2x squared. Now that run of up to 500, that is telling us what our domain is here, what our domain restriction is. I'm going to say that our domain is going to be 0 because we can't manufacture negative number of jerseys. So x is representing the number of jerseys here. X is representing the number of hockey jerseys. We can't make negative jerseys, so the lower bound is 0, and the upper bound they've given us is 500, including 500. So we've got endpoints. Okay, how many jerseys should the company produce to minimize average cost? All right, we want to minimize, okay, so we're looking for minimum values, the absolute minimum. Minimize, now, we need to be careful here. We are not minimizing this function. We are minimizing the average cost. Okay, average cost. Remember, average cost is that cost function divided by x. So that's a critical thing to note here, that we are not minimizing this function. We are minimizing this. So C bar, that average cost, is going to be this whole function divided by x. 2,000 plus 10x plus 0.2x squared all over x. And that's going to be, now, we're going to be taking a derivative of this function, right? So we would rather not have it as a big quotient because that would mean we would need the quotient rule for this. Instead, let's write it as 2,000 over x plus 10x over x plus 0.2x squared over x, splitting this into 3 individual fractions. So I'll say 2,000 over x plus 10x over x is just 10, right? 10x over x. And then 0.2x squared over x is just going to be x. See how I divided each term by x individually. So the 2,000 is over x. Dividing 10x by x just cancels the x. Dividing 0.2x squared cancels one of the x's. I want to minimize this function. Okay. I'm going to have to keep erasing things. Oh, goodness. So we've got C of x, 2,000. And we've got from 0 to 500. C bar is 2,000 over x plus 10 plus 0.2. All right, let's find the minimum value for this C bar of x function. First thing, get those endpoints. Plugging in 0, well, that's undefined. Undefined because of that right there. Okay, since c bar of 0 is undefined, then I suppose that the domain that we actually want to look at for our average function is going to be not 0 to 500 including 0, but 0 to 500 excluding 0. So that means we don't need to check this endpoint because it's not actually an endpoint here. So we need to check the other side, which is 500. So c bar at 500 is going to be 2000 over 500 plus 10 plus 0.2 times 500. So I'm checking the outer endpoint there. Not having to check this one because our function isn't even defined there. This is 4 plus 10 is 14 plus a fifth of 500 is 100, so getting 114. Okay, so we have one potential extreme value here at 500, 114. That's just coming from the endpoint. I'm going to have to keep erasing just because of limited space, so feel free to pause and write down anything you need to. Okay. Next, let's take the derivative of this average cost function and set it equal to 0 and solve and find any place where our cost levels out as a minimum. Okay, derivative of this is going to be negative 2000 over x squared, that's by the power rule. Then plus 10 goes away, and then 0.2x just turns into 0.2. Cool. Okay, now set this equal to 0. Set it equal to 0 and solve for x. Solving for x here, I'll subtract negative 0 or subtract 0.2 from both sides. So I have negative 2000 over x squared equals negative 0.2. Multiplying by x squared on both sides, got to get that x out of the denominator. So I'm getting negative 2000 is equal to negative 0.2 x squared. And then I'm going to divide by this coefficient. Dividing by negative 0.2 gives me 10,000 is equal to x squared. So all of these quick calculations I'm doing, like the dividing by the decimal, just do in your calculator if you're not sure. Now square root both sides. We should get x. Now the algebra will tell us that x is plus or minus 100, but we know that negative 100 is not in our domain, right? We can't make, x is a number of jerseys. We can't make negative 100 jerseys. So we'll just say x is 100. We'll just ignore that negative value because it's not in our domain. Because our domain is 0 to 500. Okay. C bar at 100 now, I gotta find this coordinate point, is going to be 2000 over 100 plus 10 plus 0.2 times 100. That's going to give me 20 plus 10, which is 30, plus 0.5 of, that's going to be 50. That's going to be 50. So I'm getting the coordinate point 100, 50. All right. Now, the last thing I've checked endpoints, I've checked where my derivative is 0. The last thing I'm supposed to check is where is the derivative undefined. So my derivative was negative 2000 over x squared plus 0.2. My derivative is undefined at x equals 0. Okay. So does that mean we're going to get another potential extreme value? Well, let's see. Derivative is undefined at x equals 0. Normally that would mean that we've got another potential extreme value at x equals 0, but the original function is also not defined at x equals 0. So disregard this point. We can't even plug 0 into the original function, the original average cost function, right? Because of that right there. Can't plug 0 in. If our derivative is undefined at that point, but our original function is 2, then that is not going to be a point of interest for us. Okay, so now what we need to do is we need to compare these 2 points and say which one gives a lower average cost. Now remember, the x value is number of jerseys, the y value is the average cost here. So, all right, let's say it this way. X equal to 100 gives the lowest, because 50 is lower, right? 50 is lower than 114, so at x equals 100, we have the lowest average cost. Now, there's still a question about this left-hand endpoint. What is happening there? Because we can't directly check that endpoint, right? We can't plug 0 into our function. Here's the thing. We could make a graph of this function. We could do that with a graphing calculator, and we could investigate what's happening near 0. We could even use a limit and send x to 0 and evaluate that limit to see what's happening. But if we step back from this problem and look at it as a real-world application problem, do we really want to investigate our cost when we're producing almost nothing? Right? Because this is 0 jerseys. So surely that information, even if this is a low cost, that information is not going to be that useful, because if the way to minimize our cost is to just not produce anything, then why even run a business, right? Why even be in this business? So I think that this is fine without having to investigate this point where we're producing nothing. So without worrying about that left-hand endpoint, this point, x equals 100, is going to give us the lowest average cost. Producing 100 jerseys per delivery, or what was it, per run they called it, per run, minimizes our average cost. Minimizes our average cost. There we go. By the way, the average cost itself at that production level is $50. Okay, this next problem, example 2, is, let's see, we're building a rectangular enclosure for a pet rabbit against the side of a house. We have 100 feet of fencing. We want to know, what are the dimensions that will maximize area? What are the dimensions of the largest area we can enclose? Picture first. Here's the house. This is the fencing. So the thing that makes this a little tricky is the fact that we're putting it against the house. Is it a house? Let's see. Yes. So this is the house. And this is the fencing. If we were putting fencing on all 4 sides, if it wasn't against some other, like a house or a building, if we were just putting fencing on all 4 sides, the way to maximize area is just make it a square. Just make the sides equal. It gets more interesting, though, when one of those sides doesn't need fencing, right? It's that the house is creating the border for that side. Well, what do we know here? What do we know? We don't even have a function, right? We need to build the function. The sum or let's say the total fencing is equal to 100 feet. Is it feet? Yes. We're building a rectangle, so that means the perimeter of this shape, let's say that this is the length, this is the width, and then another length. We're going to have length plus width plus length will be equal to 100 feet. Say 100 there. Okay, so we've got our perimeter as length plus width plus length is equal to 100. You notice there's only one W, right? Because this width here, there's only one of those because the other side is bordered by the house. So we have this relationship, 2L plus W is equal to 100. So W is equal to 100 minus 2L. This is a critical step here. You're going to see why in a second. Okay. What are we trying to maximize here? Area, right? We're trying to maximize area. Area is equal to the product of those two sides, length times width. We need this to be a function. If we're trying to maximize area, we need a function so that we can then take its derivative and maximize it. The problem is, this is a function of two variables here, length and width. But don't we have W written in terms of L here? W can be replaced with a function of L. So now I can say area is L times 100 minus 2L. So now area is a function of L. Area is now a function of L. Is a function. That's the idea here. When you're trying to build these functions, if your function is dependent on two different things, like area of a rectangle here is dependent on length and width, you need to get one of those variables in terms of the other. That's what I did here, getting width in terms of length. That way you can write your area function, the function that you're actually trying to maximize, in terms of one letter. You have to have one letter here. Because we don't know how to take derivatives yet of functions that have two variables. That's a whole nother discussion. So I've now got area written as a function of the length. That's an L. I hope my L's aren't messing you up. That's an L. Area is a function of the length. I want to maximize this. I want to maximize this. So let's see. What do I need to think about? I need to take a derivative of this area. I'm going to use the product rule. Do I need to? How about this? How about I write A of L equals 100L minus 2L squared. Just distributing that L. It's going to make taking my derivative a bit easier. Because I'll get 100 minus 4L. Okay, set that equal to 0. 100, so I'm trying to find this maximum position. So I'm setting my derivative equal to 0. And let's see, L should be 25. There we go. See how I got that? Add 4L to both sides, then divide by 4. So L is 25. And that means width is, what was width? Width was 100 minus 2L. So that's going to be 100 minus 2 times 50. So 100 minus 50 is 50. There are the dimensions that maximize area. So we're going to have a length of 25, a width of 50, and then a length of 25. This maximizes our area. By the way, what would that area be? What is 25 times 50? All right. So the area itself, will be 1,250 feet squared. The question was asking, what are the dimensions of the largest area? So this is what we at our units here. These are both in feet. So the question wasn't asking for what is the maximum area. It was asking what are the dimensions that produce the maximum area. Something I didn't look at here is, do I have any endpoints for my function that I was trying to maximize? Or do I have any spots in the derivative where the derivative is zero? Where the derivative is undefined. I don't have any undefined spots. I'm only going to have undefined spots if I'm dividing by my input variable. That's not the only way, but that's usually the way. Here, do I have any endpoints to worry about? Is there a lower bound on what L can be and an upper bound on what L can be? Sure, there's a lower bound. You could let L be 0, but then we wouldn't have any area. Or you could let L be 100, but then you still wouldn't have any area. So we don't need to worry about the endpoints here. We don't need to worry about the endpoints. So since we don't need to worry about the endpoints, this is the only maximum value that means anything in this problem. Example 3. So we've got a company that's building baby strollers. If the company sets the price P of a stroller, if it sets the price at P, so some P, price P, then it can sell this number of strollers. Q is for quantity, 300,000. This is going to be a function of P, so minus 10P squared per year. So this is per year. What price will bring the greatest revenue? What price will bring the greatest revenue? We want to maximize revenue. Do we have revenue? We need the revenue function. We don't have it. But revenue as a function of price is equal to Q times P. We have Q. We're just going to tack a P onto this. So I'll say 300,000 minus 10P squared times P. This is Q times P. That's what revenue is. That's what revenue is. And this revenue is a function of the price. We've seen, yes, revenue is a function of the price here. And let's see, I know I'm going to be taking a derivative of this, so to make my life easier, I'm going to distribute this P. So I have 300,000 P minus 10P cubed. Okay, let's worry about the endpoints at the end. Let's get the derivative of this and set it equal to 0. So R prime of P is going to be 300,000 minus 30 P squared. This is by the power rule, just taking the derivative of this function. Set this equal to 0. Solving for P, you should have subtracting 300,000 from both sides, dividing by negative 30, and then taking the square root, we're getting P is plus or minus 100. Obviously, we don't want to charge negative $100. That would mean we're giving people $100 to take our strollers. Or what is it? Strollers, yes. So we're going to disregard that negative 100. Okay, let's plug that into the revenue function, which was R of P is 300,000 P minus 10P cubed. This was our revenue function, so plug 100 into that. Okay, that's gonna be and then I'm not gonna make you sit through this. Okay, $20 million. That's what our maximum revenue. Well, one of the potential spots for our maximum revenue. Now, let's think about the domain of this revenue function. Clearly, we want P to be greater than 0, right? We don't want to charge negative money, right? So we want P to be greater than 0. Also, though, we want Q to be greater than or equal to 0, our quantity, right? The quantity we're producing, we don't want to produce negative items, so we want this to be greater than or equal to 0. What does this mean for the price? What does this mean for price? Because Q is a function of P. Well, it means that if Q is greater than or equal to 0, then this function of P has to be greater than or equal to 0, because that's Q, right? This is Q. So what does this mean for P? Well, if I solve this, maybe I haven't solved an inequality in a while, but it's okay. Add 10p squared to both sides, divide by 10, and then square root both sides. When you square root both sides, you're going to have, how do we write this? Let's see. This is going to bound P between the positive and negative value that we get from square rooting both sides. It's going to bound it between these two values. So to kind of see what's going on here, think about this equation just for a minute. If x squared is less than or equal to 4, and that means I can't plug in anything bigger than 2, right? So x has to be less than or equal to 2. Say if I plugged in 3, then this would be false, right? So it has to be less than 2. But also x has to be greater than negative 2. Excuse me. Because if I plug in anything smaller than negative 2, like a negative 3 or something even smaller, then this will be false. So x has to be less than or equal to 2 and greater than or equal to negative 2. And that's what's happening here. It's just the numbers are much larger and scarier looking. So P has to be greater than negative square root of 300,000 and less than positive square root of 300,000. By the way, this simplifies to negative 100 on square root of 3 and 100 on square root of 3. This side doesn't mean anything because we already knew our price has to be positive, right? We already knew our price has to be positive. So really what we're getting from this is that our price is bounded above by 100 times square root of 3. Okay. Let's check that point. R of 100 times square root of 3. Because if we get a price or a revenue that's higher than 20 million, then that means this is actually our maximum price to maximize our price to maximize revenue. So we'll do 300,000 times P minus 10 times P cubed. So I'm plugging in this new P value that I found at an endpoint. This is an endpoint that I'm checking here. And what am I going to get from that? We will ask a calculator. And what I am getting here is an extremely small negative number. It's, I out to like 10 decimal places. 1, 2, 3, 4, 5, 6, 7, 8. For all intents and purposes, it's 0. I'm getting negative 0.000000004. Might as well be 0. This clearly does not maximize our revenue, right? This is much higher. 20 million is much higher than 0. So the point that maximizes revenue, or the price that maximizes revenue, is 100. Okay, next example. Next example is a bit heavy with the geometry. It says, so this is example 4. The Metal Can Company has an order to make cylindrical cans with a volume of 250 cubic centimeters. What should the dimensions of the can be in order to minimize the amount of metal used? This is not easy. This is not easy if you've never done this before. Let's start with what we know. Volume is equal to 250 centimeters cubed. That seems like basically all I know. I also know, though, that these are cylinders. Cylinders have a volume of pi r squared times h. Where that is r, and that is the height. So pi r squared. Pi r squared is the area of that circle, and then times the height. Okay. What am I trying to maximize? Or no, minimize. What am I trying to minimize? The amount of metal used. What does that translate to in math terms? What does that translate to? Minimizing the amount of metal used, I need to minimize the surface area. That's what I'm trying to minimize. Surface area. The surface area of a cylinder is 2 pi r h plus 2 pi r squared. Let me break this down for you. The cylinder is built from 2 circles, right, top and bottom. So this area is pi r squared, this area is pi r squared. That's this term. That's the top and the bottom. Okay, that's the top and the bottom area. This thing is the sides. If you take this side, the sides of a cylinder, and you cut it down the middle, so imagine taking a cylinder, cutting it down the middle, and then laying it out, it would be a rectangle with height h, and what would be the length of this top side? Think about that. Wouldn't it be the circumference of the circle, right? If I'm taking a circle, I'm cutting it. First of all, the circumference of this is 2 pi r, right? If I'm cutting it and I'm now laying it down flat, this distance should be the same as the circumference of the circle. That's going to be 2 pi r. How do you find the area of a rectangle? You do length times width, right, or the product of those two dimensions, which is 2 pi r h. All right, so that's where that surface area formula is coming from, in case you haven't seen it before. This is kind of similar to the example 2, because we've got a function that we want to minimize, but it's got a dependence on radius and height. It's got a dependence on 2 different things. I want to see if I can get height as a function of r, or vice versa. I could get r as a function of h, or h as a function of r. But it's going to be easier in this case to get h as a function of r. And that's going to come from this information right here. Because I know that pi r squared h is equal to 250, because that's my volume. That means that h is equal to 250 over pi r squared, just dividing this term over. That means I can rewrite s as 2 pi r times h, but h is now a function of r. H is dependent on r now. So there's 2 pi r h plus, second term, 2 pi r squared. Okay. S is now a function of r. So I can, instead of just writing S, capital S for surface area, I can write S of r, because it's now a function of r. So I used that volume that they gave me to get my h as a function of r, so that then I could get rid of this h in my surface area formula and get the function that I want to minimize as a function of a single variable. So now what I want to do is take that function, take its derivative. Should probably clean it up though before I take its derivative. I'm going to take its derivative, set it equal to 0, and find that radius value that minimizes my surface area. Before I do that though, let's clean up that S of r function. So I can clean this up a bit. The pi's will cancel, right? I got 2 times 250. That'll give me 500 in the top. Pi's cancel. R cancels with r squared, leaving me with a single r in the bottom. So that whole term cleans up to just 500 over r, which is really nice. And then plus 2 pi r squared. Nothing really to do there. Now I want to take its derivative as prime of r. That's going to be negative 500 over r squared. That's the first term. Plus 4 pi r. So r is the variable here. So I took the derivative. Now I want to set this equal to 0. Can we see it here? Yes. Negative 500 over r squared plus 4 pi r equals 0. Let's see. I'm going to multiply both terms by r squared to get rid of that r squared in the bottom. That's going to give me negative 500 plus 4 pi r cubed is equal to 0. So what I did is I multiplied both sides by r squared to get rid of this r squared in the bottom. Multiplied this by r squared, making that 4 pi r cubed. And the 0 also got multiplied by r squared, but 0 can absorb that, so it's still 0. So let's keep going with this up here. So I'll add that 500 to both sides. Solving for r here, so I'll say r cubed is 500 over 4 pi. So r is the cube root of 500 over 4 pi. That can clean up a little bit, actually quite a bit too. 500 over 4 is 125 over pi stays at the bottom. And then cube root of 125 is just 5. Oops. So r is 5 over cube root of pi. I can't get that pi out of the cube root because pi is not a perfect cube. But 125 is, cube root of 125 is just 5. So the pi is still under a cube root. Okay. Almost done. The last thing is, well, what was the problem asking for? What should the dimensions of the cans be in order to minimize the amount of metal used? Well, I've got R, but now I need H. Okay, I need H. But remember, H was equal to, oh, dang it, what was H equal to? 250 over pi R squared. That's from earlier. 250 over pi R squared. So, I've got H is equal to 250 over pi times that squared, 5 over cube root of pi all squared. Which we could clean up. You know, this would actually clean up pretty nicely. Actually, it would be 10 over cube root of pi. So we're getting that r is approximately equal to, what is 5 over cube root of pi? 3.41. And h is approximately, this is centimeters, right? Centimeters. And h is approximately 6.83 centimeters. Okay, there we go. This would be the answer. Now, something interesting about this is that you can see it here or you can see it here. H is exactly double of r, right? If you look at the approximations, you can kind of see that. Of course, there's been some rounding here. But if you look at the exact answers, this is 5 over cube root of pi. This is 10 over cube root of pi. H is exactly double of the radius. That means that this cylinder, the diameter of the cylinder, let's see if I can draw this, the diameter, which is twice the radius, this diameter is exactly the same as the height. So this distance here is the same as this distance here. That's what we're getting here. Because the radius, right, twice of the radius is its diameter. So we're getting quite a squat can. Like you've seen cans in the store. They don't look like this. They're taller than that, right? So that's an interesting thing to think about. Why would companies make cans a bit taller? And it must have something to do with not just minimizing surface area and the amount of material used to produce the can, but also probably something to do with minimizing volume for storage. If I had to guess, that's why they're not all short and squat like this. That would be my guess as to why cans aren't all this short, squat shape.